Okay. So this week we have Vito. He's from Ripple, one of the largest blockchains, and especially with institution adoption in the space. So he will going to talk about distributed ledger technologies overall, and I guess he will give a bit of insights what Ripple is building. So yeah, let's welcome him. And yeah.
All right. So we have 3 hours, right, in total, all in all, and I have an hour to do the lecture.
Yeah, exactly.
So if you have any other questions afterwards about XRP Ledger, about blockchain, we can have an interesting discussion. Don't be shy. Again, I don't bite, for the most part. So, okay, so who am I? Let's, I believe it's proper to first introduce myself. So I'm a software engineer at Ripple, and I have kind of a weird mix of expertise. On one hand, I deal with deep networking of blockchains, you know, figuring out how do we optimize how computers communicate, like TCP packets, UDP packets, network topologies, and blah, blah, blah. And this is what we're going to be talking about today primarily. And on the other hand, I work with DeFi protocols. So things like lending protocols, automated market makers, clubs. How do we make them efficient? How do we exploit them? How do we not let people exploit them? Stuff like that. And I think I'm the only proud owner of a PhD thesis entirely on XRP Ledger. Like this. No, the name XRP Ledger is even in the thesis title. So if you have a question about XRP Ledger, if I don't have the answer, at least I'll know who has the answer. So don't hesitate to come. Okay, so what are we going to cover today? So first, I want to differentiate between what is a distributed system and what is the actual decentralized and decentralized system or decentralized blockchain. What does that actually mean? Then, because I want to focus more on the deep technical part of things that are often overlooked, I'll talk about how does the blockchain network actually come to be. So how do the computers actually, well, you know, form into a public network? And then finally, when this network forms, what are the various properties of these networks and what do they affect, and what do they affect? All right, so if you don't already know, then hopefully by the end of the hour, when you'll hear the phrase decentralized public peer-to-peer network, you will know exactly precisely what each of these words mean in that particular context. So let's start at the very beginning. Networked computer systems are absolutely everywhere. Starting from the fact that you're carrying a mobile phone that allows the government, your service provider, the phone manufacturer, and every other clever, nosy person to know where you are, what you do, what you had for breakfast, lunch, and dinner. To more simple things like if you have an automated one of the little IoT devices in your home that, you know, reports to the server somewhere what the temperature is, and then you can go on your phone and change the temperature in your house while you're swimming in Alaska. Really cool. Very, very dangerous, but different kind of security conversation. So network systems are pervasive. But instead of focusing on these deep things, let's start with something simpler, something humble, a database. So I think all of you know, at least conceptually, what a database is. Very simply put, it's a piece of software with which you can interact, and to tell that piece of software, hey, here's some data, store this data, or here's how you identify the data I want. I write a query, give me this data. Cool, very simple. It's a very simple system. Well, it's not simple system, but it's a simple concept. And at the very beginning of the databases, we had a centralized database. What does that mean? Well, it means you have the software running on a single computer, and everyone who wants to interact with that software will go to that computer and do whatever they want to do with that data. All good. So we have a couple of people, they come, they interact, everything's fine. You have a couple of more people, they come, they read, they write, great, beautiful. More people, great. More people, and your database catches on fire because a single server, a single CPU, a single, processor can only handle so much traffic. It can only do so much processing. So and there's only, CPUs get only so powerful. So now what we do? Well, instead of having everything on a single computer, well, let's add more computers into the system. So maybe those guys over there, they have their part of the system that only they interact with. These guys over here have their part of the database, but as a system whole, it's one singular system. And then those two other guys, well, they're very fancy, so they get their own private instance. Cool. But altogether, this is still one unified system that, for the sake of the current conversation, there's magical pixie dust there that makes it all work. So a distributed / decentralized systems, and we'll get to decentralized part in a moment, have a couple of properties. First is that all of these servers, they are running the software autonomously. So there's no necessarily central one governor that tells everyone what to do. The second part is that these systems are asynchronous. What that means is that there's not necessarily a single clock that all of them are are following. And maybe while this database here is reading, this database here is writing. And this brings a problem of, well, how do we make sure that everyone has the same view of the current state, of the current reality? And this is where consensus algorithms come into play. The third property is that these systems are failure prone. What it means is that in our database example here, some of them can fail up to a point, and the system should still be able to run. And then finally, as these different databases are communicating with each other to agree on a common state, for example, the medium over which they're communicating is unreliable. So the actual TCP/UDP networking that you're doing, over the wire is notoriously unreliable. We as the end users don't see that because, well, there's a lot of smart software above all those layers that account for all the errors. So these systems as well need to account for all sorts of networking related errors to function correctly. Okay, to give you an official definition that is not mine, I wouldn't make such claims. A distributed system is a system where the servers of the system, where the processes, where the resources, where the data are spread apart enough, as much as is necessary for the good operation of the system, but not more, just enough, right? And you interact with these systems every single day. You listen your music through Spotify, you get your emails through Gmail, you watch your series in the evening through Netflix, and then you tweet your opinion about the latest movement on Twitter, well, X. And all of these systems, there are hundreds and hundreds of servers running behind them. That when you interact with the system, they all do their little part in the correct operations. One thing they share in common is that although there are many computers behind each of these systems, they are all owned by the same entity. So Spotify owns all of its microservices, all of its servers. Google, Netflix, Twitter, same idea applies. So what that means is that they can make certain security assumptions about the sanctum in which their servers are operated. And this is very important, because what if we don't want that? What if we want a system where I own my information, where I own my my server, where I own my piece of software and nobody else does. So now imagine that these guys, that is their server. These guys, this is their server. I muted myself. Okay. So they own this part of the system, all of the data, all the interactions, and so on and so forth. Right? So not only we need some magical glue that makes everything synchronized and running smoothly with a common state. Now also that magical glue, the consensus protocol, needs to make very strict security and trust assumptions. And the trust assumptions they make is basically, I don't trust anybody. So whatever is happening in the system, I double verify their cryptographic algorithms to make sure that if someone is misbehaving, I can figure out that something is not going right. So to give you a kind of a more formal definition of what a decentralized system is now. Oh, sorry. Well, that's the magical glue that keeps everything together. A decentralized system is where the distribution of processing and resources is necessary for the correct behavior of the system. So now, to wrap here, to kind of better visualize this concept is, take Bitcoin, for example, right? If I owned all of the servers of Bitcoin, would you trust Bitcoin? Of course not. You wouldn't trust it because since I own all of the servers, I own all of the decision making, I can go and tweak whatever I can. So the system now has to have a lot of participants, a lot of heterogeneous ownership to make sure that the system is operating correctly. And the blockchain is not the only kind of system like that, where the resources have to be spread all over the shop for the system to work correctly. Another good example is federated learning. Does anyone know what federated learning is? Don't be shy, I will not bite. I will not judge if you don't. Okay, so federated learning is a really cool concept in machine learning. So imagine you have two competing corporations, right? So corporation Acme Corp and Foo Corp, right? They're in the same domain. They do not want to share their data, but they know that they will benefit if they train the same machine learning model using their data. So the question is, well, how do we train a common machine learning model without sharing with each other our data? And this is where federated learning comes in. So it's a set of distributed machine learning algorithms that allows us to train a model without actually revealing the data we have to each other. So the data stays put. And then, of course, as you all know, as the distributed ledger technologies, blockchain. So to recap and a little bit summarize the differences between centralized, distributed, and decentralized, I could have just shown you this table and would have, but then I would have had less things to say. So anyway, so with a centralized system, the input is coming from multiple sources. So you have a bunch of users interacting with the same data, but your storage, your processing, your output, and the ownership comes from one place. With a distributed system, we still have multiple inputs, but now your processing, your storage, and your output comes from multiple different computers in the network. And then but still the control is still part of the same, still one node, And then finally, with the decentralized system, we have the final bit of the puzzle where now we have multiple owners in the system, and those owners do or do not necessarily trust each other. All right. By the way, if you have any questions at any point, I should have maybe started with this, but just raise your hand and then don't, so that I don't go on and on and on. Yes, awesome.
Yeah, is storage a decentralized system or a distributed system?
Sorry?
Torrent.
Torrent. Torrent. Ooh, that is an excellent question. It is definitely distributed because, the data is distributed across multiple servers. And I assume in torrent, I don't know too many details about the actual inner workings of the protocol, but I'd argue that it is also decentralized because you can't make any trust assumptions. You can't trust whoever you're downloading the data from. So you might have to do checksums or some verification to make sure that someone doesn't slip something into you. So I'd argue it's a decentralized system, although there's no consensus per se because. And I don't know enough about torrent to make any further comments. But yeah, I would argue that it's a decentralized system. And Nick is nodding his head, so I think I got it right.
I think it's more decentralized than a lot of the blockchains out there.
Fair enough. Fair enough. And we'll get to that specifically that point later. Okay, moving on. So now everyone knows distributed, decentralized, and centralized. What's next? Okay, so what is a system architecture, right? So it's a set of rules. It's a set of kind of properties that allows us to describe the logical structure, the logical and or the physical structure of the system we're talking about. So one system that everyone, again, interacts on every single day is something that we can call layer architecture, where, for example, you click on a website. What that'll do is the request will go from your browser. It will go to a server that is serving the application, the PHP code, the JavaScript code, whatever. Then it will go into a database, do whatever it has to do in the database, go back a layer, and then go back to you. That's why a lot of websites are simply called, fancy database wrappers that allow us to, have a more user-friendly representation of data. Another kind of system we have is a peer-to-peer system. So now in the system, we have a lot of different servers that are interconnected with each other, a lot of different actors that are interconnected to each other, and the communication is often transitive. What that means is that, a friend of my friend may be my friend. So for example, if I know John and John knows Alice, and I want to send a message to Alice, I'll send the message to John, and then John will forward it to Alice. That is the basis of peer-to-peer network. Because now, if you imagine if you have a system of, I don't know, 1,000 friends, 1,000 computers, right? It is really, really difficult to know 1,000 people. And it is really, really difficult for a server to have 999 connections. And if you, for example, take real distributed systems like Bitcoin and Ethereum, where you have tens and tens of thousands of servers, so now you can't have everyone connecting to everyone, and so you rely on a lot of these transitive relationships. Okay, how does communication happen in these kind of systems? So imagine Alice, the source of the message, wants to send a photo of a cat, because that's what the internet is for, sharing funny cat pictures. Wants to send this funny picture to Bob. But Alice doesn't necessarily know where Bob is. Maybe Alice knows a logical identifier of Bob, but not necessarily the IP address or anything else. So what Alice does is that, says, I don't know where Bob is, but maybe this person here knows where Bob is, or maybe they know someone who knows where Bob is. Anyway, here's a picture of the cat. Have at it. And the other person, the other server, receives the picture of the cat, says, this is not for me. I don't know what to do with it. Have at it. And that is repeated across the whole chain internet. Of course, the communication doesn't necessarily have to have a destination. So maybe I want to send a message to everybody in the system. Same logic applies. I'll send a message to everyone I know, then everyone, then each server will do the same, and so on and so forth, until the message reaches everybody. But the whole point is that, again, communication is transitive. So I send something to someone, then they forward it, they forward it, they forward it. Okay. So moving on. We know centralization. We know a little bit about architecture, and we know a little bit about high principle, high ideas of communication in distributed systems. So now, how does the actually network come to be? How did Bitcoin came to be as a, how come Bitcoin has 50,000 servers, and how do I join Bitcoin? What is the logic behind it? How does it actually? So the first step when you're joining a network, a public, one thing I should have made clear is that I'm specifically talking about public networks where anyone can join and anyone can leave. With private networks, then it's completely, proprietary. There are different ways to do private network discovery. I'm specifically talking about public networks. So how do you join a Bitcoin network when you don't know anybody on the Bitcoin network? And this also applies for Ethereum. This also applies for XRP Ledger, Solana, Polkadot, ad infinitum. So somewhere in the configuration of the actual software, maybe somewhere on the internet, you'll have a bunch of addresses to servers that are called bootstrap nodes. And these servers, in essence, act as your gateways into the network. And the way it tends to work is that, well, you connect to these bootstrap nodes, and then these bootstrap nodes, will say, well, I'm a very busy server because everyone always connects to me. So here's a bunch of alternative IP addresses you can connect to. Go at it. Maybe I'll give you 10, 20 seconds for you to establish more connections, but eventually I'll disconnect you because bootstrap nodes are very busy, so they don't want to be overloaded all the time. And then this process will repeat until the number of connections a server desires is saturated. Why is it important for a server to have a lot of connections in a public system? I won't bite anyone. I'll pick someone, I'll point a finger at someone. So somebody better volunteer. I choose you. Yes. Why is it important in a public system, in a public network, like a blockchain, for a server to have more than one connection? Spot on, exactly. So that's exactly the reason, so that I have some redundancy in my networking. But on top of that, we also want to have a lot of connectivity, well, for security reasons. Because, for example, imagine, I'm on Bitcoin and I'm only connected to John, and I have no idea who John is. And now if John is my only connection, whatever John tells me that's happening in the network, well, I don't know if that's true. Maybe John is lying. How do I know that? So that's why you want to have a lot. That's why with your server, you want to have a healthy number. And healthy is kind of there's no official definition. Healthy is 5 servers. So for example, in XRP Ledger, it's by default at least 15 different connections. So you want to have a healthy number of peers so that you're always aware. You have multiple people, multiple servers saying to you what's going on. And if suddenly I'm seeing that John is always sending something different from everybody else, well, it is not a definitive proof that John is being malicious. Maybe actually the opposite. John is good and everyone else is lying. But majority of it. So chances are that John is lying. And of course, the more peers you have, the bigger your peer pool, the more reliable information you have, whether some peer is good or some peers. Okay, so yeah, we covered everything here. Peer discovery. Okay, so peer discovery refers to let's take a small step back to our bootstrap node. Peer discovery is the logic with which a server actually finds new peers. Because the bootstrap servers, it doesn't know everybody in the network. It needs to know that, okay, that server can accept connections, that server can accept connections, that server cannot accept connections. So the logic by which peers discover or advertise the ability to accept more connections is called peer discovery protocol. And in general, they come in two flavors. One flavor I'll describe now. The other flavor I'll leave for you to do as a homework that I believe Tammy will double check to make sure everyone got that correct. I'm joking, Tammy will not do that. It's for your own edification. So the two general flavors is basically through peer messaging exchanges, where if I have a open incoming connection slots, I say that to my peers, hey, I can accept more connections, and then those peers propagate those messages, so on and so forth. And then the other one are distributed hash tables. That's your homework to figure out what that is and how that works. And then manual peer configuration. So manual peer configuration is basically, well, instead of allowing some algorithm to decide who to connect, in the configuration, I manually by hand enter the IP address. But that's too simple. That's not interesting. And distributed hash tables are your home. So okay, what is the problem? So let's say I'm a server, right? I can accept incoming connections, and I send advertisements to the network saying that, well, hey, I can connect. What is there are several problems. What are these problems with such an approach? What are the limitations? What are the gotchas? I'll ask you. You can name one, and then I'll ask someone else another.
I think the most important part is how do we trust it and how do we prove it in to us? Also, how like what is the like how we handle security and protecting data from other people to stop them from doing. I think these two main issues.
So you're saying it's security and identity.
Yeah.
Good. Anyone has anything else to volunteer? I'll pick somebody. I'll make somebody talk. Raise your hand. You.
Yeah. Actually, I still don't get the question. Can you make it in details? Like,
yeah, absolutely. If something I'm saying doesn't, it's not very clear, raise your hand. We'll get there together. Don't hesitate. So let's go back to our setup, right? So remember, I connect to the bootstrap nodes in the network. This gateway that lets me access the Bitcoin blockchain, for example, right? But this is only one server. And there are a couple of ways to discover other servers in the network to which I can establish connections. And one of the ways that we're discussing is something called simply advertising, where if my server here has incoming connections, right, it will send advertisements to other servers in the network saying, hey, I have connections. I can accept connections from somebody else. So that when someone joins the network looking for a connection, well, they can connect to me. And so the question is, what potential flaws, issues, and challenges do you see with such an approach? So the gentleman there said that there are two issues: identity and security. What else would you see that as a?
I think that I don't know the detail mechanism, but like if you want to take a new members into the whole system, that you want to win majority there, like they want to say yes, and it takes time, and like you have to ask every one of them, and because I don't know the details, but
Open system. So imagine this is like Bitcoin where anybody can join. There are no constraints who can join. But what you're just saying, what you're talking about right now is very, very important for private networks or hybrid networks. But that's a more advanced conversation.
So I think this is the advantages, because you don't need to to take the majority. They gonna say yes, and it's very quick.
Cool.
Yeah.
So is it correct to say that except for security, identity, everything else is great?
Yes.
Okay, cool. Does anyone else anything else they'd like to? I won't bite this. We will not. I will not give you marks. Okay, fine. I'll stop. I'll stop. I'll stop biting you. So, indeed, one definitely problem is when I say when a server gives their IP address and they claim to be somebody, how do they actually know that they are who they say they are? So first, the problem is, well, how do servers identify themselves in the network in the first place? So obviously, the number one thing is an IP address. And number two thing is in XRP Ledger, let's use XRP Ledger as an example, all servers have their own unique logical identity that is derived from a public-private key. And I assume does everyone know what the public-private key pair is? Good, okay. So from my public key, I can maybe hash it, I can encode it in some way, and from that, I can have a unique identifier that is unique for me. And unless somebody manages to break public-private key cryptography, good for them, bad for everybody else, that identity is unique. And because that is based on the public key, now we can use a cryptographic tricks to verify that indeed they are who they say they are. That indeed they have the private key that they claim to be. Or we could ask them very nicely, hey, could you give us your private key? But I don't think that will fly very well. And the way we actually verify this is basically, I'm going here deep into the weeds now. So we establish our TCP connection. There's no encryption, there's no identity. I just connect to the IP. I took that IP address through faith. Then we are upgrading that raw TCP connection where there's no encryption, there's no, everyone can see what we're doing. There's someone in the middle, they can just grab those packets and they'll see what's inside. So we need to secure it. So then we take that connection, yes?
What's the TCP?
TCP is so there are two general broad ways for computers to communicate. So you connect one cable into this computer, one cable into that computer, and they have to communicate somehow. And this communication, even if it's just two computers connected directly to each other, is very unreliable. I'm skipping a bunch of networking theory, like networking theory here, but to simplify, it's a protocol, it's a networking protocol that allows computers to communicate reliably. Meaning that if Alice sends a message to Bob, Bob is guaranteed to receive that message, and the protocol will ensure. If Alice sends messages 1, 2, 3, like literally numbers 1, 2, 3, the protocol guarantees that those messages will arrive in the order. Very, very, very simplified. An alternative is something called UDP, where basically it says, here's a message, good luck. So, for example, UDP is used in a communication where we can, so I'm getting way ahead of myself, where we can afford to lose information. So, for example, if you're streaming a video, if you lose a frame or 2 or 3, you don't care. But if you're reading financial information, it is very, very important that you receive all the data, or email, or anything, any other kind of database communication. But these connections, by default, they're plain text, roughly speaking. So then we need to secure them. So we apply a suite of networking cryptographic algorithms called TLS, transport layer security. So this allows us to encrypt whatever is going on in our conversation. So some eavesdropper, when they get they get some information out of it, they will not be able to understand what's going on because it's encrypted using public-private keys that we share, that we have. We don't share private keys. So this is a very long about way to say that once we establish a TLS connection, during this process, we can go into the internals of TLS, for example, to verify that I indeed have the private key that I claim to have. So there's a TLS private key, but on top of that, there's the XRP Ledger private key that gives us my server identity. For example, that's how we ensure that someone who they claim they are. Of course, that doesn't, you don't know who the owner of that server is, but because this is a public network, maybe we don't. Okay, so through advertisement process, another big problem is that these messages that I share are, they need to expire very quickly because, well, when I share an advertisement, someone comes and connects to me, that advertisement is already false. So it means that as this message is propagated, it also has to expire very quickly so that it's never a lie, so that I don't constantly get bombarded with attempts to connect it, since I don't have any connection. And this is also the process through which I'm getting more peers. So I connect to my Bootstrap node. My Bootstrap node says, well, here are the bunch of advertisements I got recently. Go connect to these servers. I connect to these servers. These servers says, well, here's a bunch of servers I know about, other servers I know in the net. So on and so forth, and so on and so forth. So through such a process, I'm able to establish as many connections as I desire in the network. Of course, you can't make any trust assumptions because this is the public network. You don't know who these servers are. You can't blindly trust them. You need to verify everything. Okay, so now we know how this network comes to be. There's this expectation that when you're talking with people, they think that a decentralized system looks something like that, meaning that everybody is equal, everybody is the same, power to us. In reality, that is never the case. In reality, decentralized systems look like this. You have a couple of big nodes that have a lot of connections, a couple of a little bit more medium nodes, and a bunch of tiny nodes. And this is in essence trying. Blockchain is not unique. This is dictated across the entirety of the universe. So for example, 20% of stars hold 80% of mass. 20% of people have 80% of wealth, or maybe more like 1% of people have 99% of wealth, but economics class, not blockchain class. My dad used to always tell this to me, you know, from 20% of effort, you get 80% of results, and so on and so forth. So there's the way to think about it is naturally centralized. It is not decentralized, not where everybody is equal. And even if we look at the other blockchains, so for example, in Bitcoin, where you have miners that are producing blocks, right? Some have simply more resources, more money to run more servers, to have higher hash rates, to have more mining power. When we go to Ethereum, someone has more money, someone can have more staking power. They'll be able to, they will, by nature of staking algorithm, they'll have a higher probability to be the one that will determine the next block. It's absolutely normal. Decentralized systems is not where everyone is equal. Decentralized system is where some are more equal than others. So that's just okay. Right. Final thing, topology. Of course, that's why I said that. And the same logic applies also to the topology of the network. So the topology is the logical structure that these computers form when they connect to each other. And the structure affects quite a few things in the network. And I believe this is the last bit that we'll cover. So for example, this is how XRP Ledger looked like in 2020. I should update these slides. They're a little bit dated at this point, but same idea still applies. So you have a lot of servers that are, you know, tiny, and you have big servers in the center that have a lot of connections coming in. I didn't introduce what XRP Ledger is. So XRP Ledger is one of the, at this point, top 3 blockchains by value. Market cap. Thank you. And it has couple of features that, in its infancy, really made it shine. These days, it's more about so what, but still, they're important aspects. So first is the number of transactions that it can handle. So the numbers around varies between like 1,000 to 1,500, depending in which circles you ask. That's how many transactions it can handle. Then it takes about 3 to 5 seconds for a transaction to be confirmed. What that means is that when I submit my transaction, it gets propagated through the network, goes through the consensus protocol, and finally gets validated and approved in the new ledger. And that entire process takes 3 to 5 seconds. Like pressing random things, and it is notoriously cheap. Even now, where the price of XRP has, I think it has more than tripled in the last year and a half. A single transaction costs like a fraction of a cent. It's super cheap. So if you have use cases where you need to submit a lot of transactions, if you're doing a lot of payments or trading doing a lot of trading, it's a great blockchain for that because the costs are very low. And on top of that, one of the ethos of the blockchain is that the best incentive is no incentive. So all of these fees, they don't go to somebody, they're burnt. As a result, this means that because they're burned, they don't go to anybody. There are no incentives to be malicious. There are no incentives to start manipulating and doing good, naughty things that we can do on Ethereum, for example. And then the final thing that sets it apart is the consensus protocol it uses. So Bitcoin, Ethereum, they use a competitive consensus algorithm. What that means is that someone who has most of a certain resource has a more likelihood to be the one that will determine which one is the next block. So in Bitcoin, it's mining power. Whoever has more computers, more graphics cards. And on Ethereum, it's whoever has deeper pockets. And on XRP Ledger, it uses voting-based consensus algorithm. So what that means is that the servers who are making the decisions, they're no longer competing against each other, they're collaborating. So they're voting to say, well, okay, we all think that these are the next transactions that have to go into the next ledger. I'm grossly oversimplifying the consensus protocol of XRP Ledger, but that's an entire lecture of its own. So, but if you have questions, we can do it after the lecture. Okay, so how does everything work that we just talked through on XRP Ledger? So all servers have to make outgoing connections to the network to be able to participate, and be nice enough optionally accept incoming connection. This is mandatory. This is optional. Then when they connect over these connections, they do what we just discussed earlier on, advertisements. So they send their identifier, derived from the public key, the port, the IP address to which they connect, and the hop count. Hop count is basically, well, how far away the server is from me logically, meaning that through how many logical hops did the message have to go through to reach me. And with this information, we can then, the server can make decisions. Okay, maybe I want to connect to servers that are very far away to make the whole network smaller, and we'll see why that is important in a second. So yeah, and once you connect over those connections, there's a bunch of communication that happens that is necessary to maintain the life of the network, such as, your old school ping pong, to verify that this connection is still okay. The server there is still listening. So we covered this. We covered how we already also covered how the peer discovery works and how servers connect. And now finally, once they interconnect, form this logical structure of XRP Ledger peer-to-peer network. And this topology affects very important aspects of the network. First is the ability of the network itself to survive failures. So remember, at the very, very beginning, I said that a distributed or a decentralized system is a system in which any participant can go offline, and the system has to operate. And there's, of course, a logic, there is a logical limit to how many servers have to go down when the system stops working. And the other property is message propagation time. So when I submit my transaction, it is in my best interest that that transaction reaches all validators as quickly as possible. The reason that is important is that if I want my transaction to be included in the next ledger as soon as possible, so it goes through the consensus and gets validated. If I'm making a big payment to somebody, that payment goes through, it gets validated as quick as possible. So message propagation is also important. The other thing is that the final property is when the servers are communicating, how much emission, how much unnecessary traffic they generate. So if we go back to the sharing cat pictures example, since every server is forwarding a message to every other server, that is incredibly inefficient algorithm, but is incredibly effective because it guarantees that the message will reach everybody And not only that, it will reach everybody through the quickest path. Okay, so let's add some terms to the ability to survive attacks. So robustness is the network's ability to continue providing its services despite missing some of its nodes. And then we can express it very specifically, but maybe for the conversation it doesn't matter. The way we can imagine it is, so imagine we have our network, right? And we start plucking nodes one by one. And because we are set on making as much damage to the network, we are targeting nodes that have the most number of connections. So we remove one node, another one, and suddenly our network is incredibly fragmented, and it can no longer do whatever it has to do. So what we want to know is that, well, how many nodes in the XRP ledger have to fail until the network can, well, stop functioning? So at its time, this was about 2022, maybe today the number is about 10%. So 9 to 10% of the network servers have to fail until, and after that point, the network will no longer be able to work. Lucky for us, 10% of XRP Ledger nodes still equates to 100 servers. And for 100 servers to just randomly fail or be targeted to take down takes a lot of resources. And through the help of a common prefix, we're making it even harder and harder to do that. So very tough to do. Oh, there's an example missing here. Okay. But remember, yes, tell me.
Yeah, so like this case about the robustness of the network, is this like unique to the XRP ledger only, or it should be like applicable to all the decentralized?
This is applicable. So the percentage is unique to XRP ledger. The principle is applicable to any decentralized system. So for example, on Bitcoin, XRP ledger is very easy to infer how the network looks like by design. Bitcoin and Ethereum, they put a lot of effort to obscure the topology. But as you'll ask security engineers, security through obscurity is no security, because someone will figure out how to infer the data. So this percentage on Ethereum and Bitcoin is like 1 to 2%. But the problem is that Bitcoin and Ethereum networks are 10 times greater. So XRP Ledger has roughly 1,000 nodes. Bitcoin and Ethereum are, again, as estimates, between 10 to 50,000 nodes. So although it's 1 to 2%, it's still a lot of computers. So they're fine. Okay. Message propagation delay. How long does it take for a message to pass through? So the best way to think about it is, imagine the worst case scenario where you have a network where all the servers are just connected one to another, forming one line. Problem number one is that this is incredibly brittle network. One connection drops and the network is fully partitioned, but it's also incredibly slow, because if the message has to go from the source message to the destination message, well, you can see there are 3 hops. Each hop adds a delay. No good. The ideal world is where all the servers are connected to each other. So when I need to send a message, it immediately arrives to everybody that it needs to arrive to. This is good, and it's a very, very fine approach for very small systems, for very small networks. But if you take XRP Ledger, each server maintaining 999 connections, that is a lot to ask. On Bitcoin, maintaining 49,999 connections, you will quickly run out of port numbers that way, simply. So we need some kind of a balance between everyone, being connected in a single line and everyone being connected to everybody. Right. So what we see about XRP Ledger and other similar decentralized systems is that, as we already also saw in the example with the, the fact that in decentralized systems you have some nodes, a few nodes with a lot of connections and fewer nodes with medium connections and so on and so forth. The same rule, the same law applies to XRP Ledger. So what we see, so on the top we have outgoing connections. So the number of connections a server establishes to everybody else, and a number of connections that a server accepts from others. So, for example, this outlier here is one server that was incredibly naughty, connecting to more than 150 peers. That is a lot of connections. Similarly, we only have one server that had 300 incoming connections. Majority of them had between 0 and 10. It makes sense because if you're starting to accept incoming connections, you need more resources. And since there's no direct incentive to do that in the network, since there's no incentive, people tend to do that out of their own heart, out of the goodness of their heart, and people don't do it as much as they should. But again, the point is, XRP Ledger is just like any other decentralized system. A few nodes with a lot of connections, and a lot of nodes with very, very few connections. Okay. Final bit of information, I promise, and then we're done. I see there's snacks waiting behind us. Message redundancy. What is that? So again, going back to the kitten example, now we can give that algorithm a name. Flooding or broadcasting algorithm. It means that, again, when I have a message, I send it to everyone else. When I receive a message from someone, I will send it to everyone else except the one who sent it originally, and so on and so forth. So what that means in reality is that if I have 100 peers, I will receive 99 copies of the same message. So it's incredibly inefficient algorithm. But by the same nature, because the message will explore every single possible path in the network, so every single way to reach one node, it will explore every single way to reach each server in the network. It was also the most effective. So it guarantees that the message will reach everyone else as quick as possible. So then it's a question of trade-off. What is more important for us, efficiency or effectiveness? And how do we strike a balance? And this is just an illustration how that happens. I had a lot of time on my hands making these slides at some point. Okay. So start wrapping things up. Peer discovery affects the logical structure of the network. But the logical structure of the network affects how robust the network is, how well it survives failures, how effectively messages disseminate in the network, and also how efficient the network is, how much noise does it create. I should have mentioned this earlier. The reason why it's important for us to think about message redundancy is that, well, again, if we go back to our 100 peers, I'll actually really need to process that one unique message. But because I'm getting 99, but because of these other 99s, all of these resources that I spend processing them are wasted. So really, if we improve the efficiency, we also reduce costs for operators that are running these servers. And on a network like XRP Ledger, where there are no innate incentives, the best we can do as engineers is to make the costs of running the servers as low as possible. Okay, the light is there. The light at the end of the tunnel is there. So we know what are centralized, distributed, and decentralized systems. Distributed systems are the systems that are spread sufficiently, just enough for the system to operate correctly, and decentralized systems where distribution is necessary for the correct operation. We understand public peer-to-peer networks, how the network comes to be, how servers discover each other. Remember, go and have a read about distributed hash tables. It's a fascinating algorithm. And then that decentralized systems are naturally centralized. And then, yet again, these systems have logical structure called topology, which affects a bunch of important parts of the network. Hey, and we're only 8 minutes over time. That's all I have for you today. Questions? Yes. Oh, thank you.
Yeah, so the question is like in practical systems, you said like decentralized systems are inclined more towards being centralized, like some nodes becoming more centralized. And so what is the main difference between distributed and decentralized? Like they both behave in the same way, except control. And have we seen like any examples of institutions manipulating that control to like force transactions or doing something like that, which is why we created decentralized systems?
Nick, I'll need you to refresh my memory. We spoke about this on Monday. What was that blockchain? With the 51%?
Oh, Monero.
Monero. So a very good example of what you asked about natural decentralization comes from very recent example of Monero. Monero is a type of blockchain very famous for its privacy and confidentiality guarantees. One thing that happened to it recently, to the cause of natural centralization, is something called the 51% attack, which means that one entity in the entirety of the network owned 51% of mining power. And then that means that then they can start doing whatever they want with the blockchain, and nobody can stop. So this is an example of can someone do something to manipulate the network to own a lot of power? In theory, yes. For small networks like Monero, although it's not such a small network, it's possible. For Bitcoin, forget about it, because the financial cost to run to hold more than 51% of mining power outweighs any financial benefit that you could have. I'll get to your second half of the question of distributed systems. Since distributed systems are owned by a single control, they're private in nature. Means that not everyone can connect it, or maybe they can connect it, but only to read it, never to write it. So really, in that case, because it's a closed system, there are very different internal security assumptions. Topology is not the most important consideration in that.
So like the Swift system is a distributed system.
Yes, very. Yes, Swift, since Swift is, that is I'm stumped. That is a very good question. Yes, so hold on. So Swift is a protocol, right? First and foremost. And Nick, I need you to keep me honest here, because I'm treading on ground that I'm not 100% familiar with. So Swift is a financial protocol, and there's a company behind it. And that company charges fees whenever you're making bank transfers. But people running on that protocol, there are a bunch of different banks. But you need to be a somewhat trusted bank to participate in the SWIFT network. So, for example, Russian banks were kicked out of SWIFT as part of sanctions. It's a distributed system because of this security assumption, I would argue. And that there's a central entity that controls, quote unquote, controls the protocol to which all the fees go to.
Also, the SWIFT entity is the only one that can settle transactions. So banks can do their part, but eventually the SWIFT network has to settle transactions that is controlled by the SWIFT entity.
Yeah.
So that's another way we can say it's distributed but not decentralized.
Really good question. That might be in your test at the end of the year. Yes.
Like you said, XP Ledger is much cheaper for the transaction fee. But I search on the internet, it's because it's without a work of proof.
Yes.
And so, like without these things, how can we attract enough like nodes and the servers to join this internet? And yes, that's my question.
So your question, in essence, is since the blockchain itself does not have explicit incentives such as mining rewards,
Yes.
why would anyone participate in the first place? That is a really, really good question. So ultimately, it's because they have business needs that the blockchain meets. So for them, it makes sense from business perspective to run their own infrastructure. So if I'm, I don't know, if I'm running a trading firm that trades on the decentralized exchange, I'm making money on the blockchain. So I'll also, it's in my interest that the blockchain is healthy. So I will also run infrastructure to contribute to the health of the system. That is ultimately the kind of the fundamental incentive. That's not explicit, is that for you, it's important that the system is healthy, so you'll contribute to the health of the system. Does that answer your question?
I still don't get it.
So imagine this way. Let's say I have a business, and that business makes money on XRP Ledger. Without XRP Ledger, I would have no business.
Yeah.
So it is in my best interest that the blockchain is running, right? Because no blockchain, no business. So I need to make sure, do my part that the blockchain is running.
Yeah.
And when you have a lot of these different entities that are really vested in the blockchain, that really want the blockchain to work and do its thing, the incentive is implicit. The incentive comes not from the algorithm, but from the cryptocurrency itself, for example, or the crypto or the DeFi system, or whatever you're doing with the system that drives value to you.
Okay.
Also, it's important to not discredit enthusiasm and research and academia but again, all of these are implicit.
So is that like common people? It's not a big business company. Everybody can join.
Yes, everybody can join. So, for example, in the consensus protocol, you have validators, servers that make decisions ran by huge companies like Ripple, like other banks. Although you have validators run by universities, or you have validators run by individual community members.
But like without the incentive and everybody they want just why I should do the work. I just can look up the information from another nodes, let others do the job.
But then you're trusting others.
Yeah. But like in blockchain, there is no trust.
Exactly.
Yes.
So imagine let's go back to the example of multi-million-dollar business that is trading on XRP Ledger, right?
Yeah.
So if if I don't have my own infrastructure and I submit all of my transactions to another data through another server that is not owned by me, what guarantees do I have that they will not just discard my transactions because they're my competitor? Or maybe they were bribed by my competitor to discard my transaction. So it is important for my business that is we have servers, we have our own part of the infrastructure that we know, okay, this is safe.
But like, if they think the majority is big enough and it's trustworthy, because like they
But you cannot make this assumption. You cannot make this assumption that all of these other ones are trust, because at the end of the day, you don't know who other ones are. And because you don't know who everybody else is, maybe they'll censor me, maybe they will not. Or maybe they'll tell me that I have $5 million, where in fact I have none, or vice versa. So you really want the source of truth that you can trust in the system, which is yourself.
So like you think the proof of work is not essential for a blockchain, like in Bitcoin.
Proof of work, proof of stake, it's just a type of algorithm that these systems use to agree on what is the truth, what is the common state for this entire network. It's just a type of algorithm, whereas XRP Ledger uses a different type where servers vote and follow different process to reach this. The end result is the same. It's just they choose different paths and different mechanisms to get there. Really, really good question. Really good. Sorry, I thought you were lifting your hand. Yes.
Probably add to that. I think with regard to trust, more like a comment. I think there's some basic assumption that for each protocol, you want to assume a percentage of the honest. There's a threshold there, so that's kind of course, the lower the threshold, the arguably perhaps the better protocol it will be. The higher the threshold, if you have to assume that 90% of the participants are honest, that's a weaker protocol than you only have to assume 10% of the participants are honest. But I think you wouldn't trust a protocol with the assumption that no participants are not honest whatsoever. It's just there's some assumptions there just to add to what you were saying. That's
fair enough. That is a very, very important distinction. Yeah, if you can't trust anyone in the system, well, can't trust the system. You look like you have a question. So either everyone else either understood everything or didn't understand anything. Yes.
It's not related to
That's fine.
as a software engineer at Liverpool, like what mainly are your daily tasks playing involved?